Hello, everyone. I'm Dr. Poonam Yadav. I'm an assistant professor in computer science department at University of York, UK. And I'm also chair of ACMW UK chapter. ACMW UK chapter is Women in Computer Science in UK. And today I'm going to talk about Internet of Things. I'm working in Internet of Things from last 15 years. And today I'm really excited to share with you all a different perspective of Internet of Things from both user and a system. We use many IoT devices in our day-to-day life, and that's our view from a user. Whereas some of us working in computer science and technology and are backbone of many of these IoT technologies, and how we see IoT from a different view is called a system view. So before I'll start, let's start with IoT in first. This talk, I'm going to talk about two things. The first, I will talk about both user view and system view. And then second part of the talk, I will give you a bit of insights how to use fingerprinting for IoT cybersecurity. So let's start with what is Internet of Things. So you can see Internet of Things describes network of physical objects, things that are embedded with sensors, softwares, computation, and communication technologies. And the purpose of communication technologies is to connect with other data devices and systems for exchanging data over the internet. The actual term Internet of Things was coined by Kevin Aston in 1999. And you can see from last 20 years, different technologies have evolved with a rapid speed, and now we can see full-fledged deployment of many IoT applications worldwide. On the right-hand side here, you can see we have applications of IoT in different domains, whether it's a smart home or a smart industry or smart agriculture or smart cities. So you can see IoTs everywhere. The basic components here I already talk about is at the end device is sensors or actuators and some computation and communication. So there are two different views of an IoT ecosystem. One is a user view and second is a system view. When we talk about user, I'm going to talk about how as an end user, I see a IoT product. And in the system view, I will be giving my views how as a software engineer, I see IoT product. From a user view, there are three main metrics which matters to a user, apart from the cost, certainly. First is utility, second is usability, and third is trust and security. So when we talk about utility is a matrix which defines what value this IoT product or device will bring to me as a user, how useful it will be to me. Whereas usability is whether I can use this device, even though it provides lots of functionality, but there are design issues or security issues, I don't want to use it. And finally is the trust and security. How much I trust this device or how secure it is. That defines a trust and security view of an IoT device. So let's talk about something about user view. So So in user view, as we talk about utility, utility is quite a perceived as a personal preference. So, for example, an if I'm using a smartwatch, it may have a different utility to me as compared to my household members or someone else. So, utility is quite different for a same product, and which will be varied based on age group, gender, geography of the people who are using those products, in even environments and settings and different roles. To understand it a little bit more, a formal study has been conducted in last couple of years, and I'm giving here is summary of these two studies. First was the first study. Um, uh, in the first study, the researchers found that the participants rated these different services in their preference. For example, they found proximity services or as a first priority, then home automation, then healthcare and well-being. Where in the case study 2, they found healthcare, security management, home automation, and energy consumption management as a second, as their preferences. And we can see that because these two studies were asking user view on the same IoT products, same range of IoT products, we could see how preferences change from one study to other study. And because their participants were different, they were different age groups, they were different genders, they were different, even geographical areas were different. So second is, I would like to give a little bit about the usability of the product. Out of those participants, 74% user said that it's very hard to use IoT because there are so many applications. When we talk about applications, say they were confused which services they should use, which IoT product they will pick for those services, and so on. So we can clearly see that that diversity of IoT ecosystem is quite confusing for the users. And the second thing I think they raised a concern is about incompatibility issue, which means that 20% of users found it is useless to buy objects that are not compatible with all type of computers and smartphones. Every time you buy a new IoT product, if that requires your new adapters, that if that requires you to buy new set up a new routers or new communication media, people are a little bit reluctant to use those IoT devices and find it hard. So usability point of view, incompatibility issues is one of the major concerns. Finally, is the trust and security. So as I said, trust is basically an attitude towards adapting the technologies, whereas a security is a real measurement of the robustness of the system against cybersecurity attack. Trust, therefore, is just not taken into consideration security, but it also takes into consideration, for example, reliability and resilience and robustness of the system. And this is one of my research area where I'm investigating a lot about how to build resilient IoT ecosystem, and so that users trust their IoT product more. Many users in the study, when we ask them about cybersecurity, they have some of these concerns, like who will be the most affected, if something goes wrong with your my IT product, who will be responsible, and should we trust the connected objects? So these are the number of research questions all the researchers and industry, IoT industry is looking to find out answers for their users. And some of these questions feed into the way how we design the IoT products. And those are main concerns in our system view. So let's have a look here in how as a researcher and also as a system engineer, how I view IoT ecosystem from end to end. So in the first hand, we could see there are IoT devices which we directly interact with. These IoT devices could be used in a home environment, or these IoT devices are used in smart industries, agriculture, or in smart railways, or autonomous vehicle could be in one of the IoT device. What they do is they sense the data from their environment, so they are quite pervasive, and they do some local computation and then sends the data over to the cloud or a server for a processing. So gateway is another intermediate next step, where it is the gateway responsibility to connect these IoT devices to the rest of the internet. There are different technologies has been used to connect these IoT devices to gateway. These could be Bluetooth, they could be Wi-Fi, it could be Zigbee, LoRa, Sigfox. There are different other communication channels could be used to connect with the gateway, and then gateway to cellular network or a broadband. Maybe it's a wired or wireless communication. Finally, the data bridges to server in cloud, and where you do all the analytics or data aggregation and find the useful data, which you can see the summaries or events on your mobile phones or application on a desktop or web applications. If a user decide to take an action based on the data which they are receiving, the command goes back direct from in a reverse order from a mobile application directly to an IoT devices. So this is this kind of a system view, and you can see there are different technologies we need to build a system. We need software engineers, we need radio engineers, network engineers, IoT devices engineers at the low end, which is mostly computing devices and all. And when we talk about number of terminologies here, we use, for example, edge computing, where you say most of the computation which you do on the IoT data, either at a gateway level or near to the IoT devices, instead of doing it at a server or cloud. When you talk about fog computing, the one other terminology, we say, okay, most of the data we do process at somewhere in between gateway and server cloud in the network towards the IoT devices, rather than having a total different end of the cloud and server. So going from this, that was my take on user and system view of an IoT ecosystem. Now, one of the things I would like to present today is an IoT device fingerprinting in this ecosystem. So let's begin with what is fingerprinting in first place. So fingerprinting is a process of identifying a device or device type based on its intrinsic or behavioral property. When I say unique or intrinsic property, it means something you cannot change about the device. So, and the behavioral property is the way a device is behaving over time period, and you capture the behavior. When we talk about behavior, it could be the way it updates the software, the way it does the logging mechanism, the latency within the system, or you capture the way it sends the traffic out of it to the network. So you are analyzing the network traffic. There are different ways to capture the behavior of a device. So when we generate a fingerprint of an IoT device, we look for three main properties of that fingerprinting. First part is the unique identity property of the fingerprint. So whatever fingerprint you create, that has to be unique for that device. could uniquely identify that device. Second is the integrity property, that fingerprint must be impossible or at least difficult to forge. You cannot tamper the fingerprint once you create. And finally is the reproducibility property. The features used in the fingerprinting process must be stable, especially in the presence of environmental interferences or changes or mobility. So reproducibility property plays an important role in the usefulness of those fingerprints and validity of those fingerprints. So we have to keep in mind when we create a fingerprint that all these three properties are met. So now the next question is how we can use this fingerprint, and especially in cybersecurity. So first, every IoT device in the network needs an identity. And to create this unique identity for that devices, we can use this fingerprint to create a unique identity of the device. And specifically if this fingerprint we are creating using the intrinsic property of the device, for example, device property, based on hardware device property, then it uniquely identify that device. Whereas we can use those identity which we created using a fingerprint used in the authentication for generating authentication keys for the device so that this device can connect to the other devices in the network, and there's a proper authentication mechanism. And finally is this fingerprinting can be used as a device anomalous behavior tracking for tracking anomalous behavior of IoT devices in the network. So if something goes wrong with the device, and if the traffic which is generated by this device or the way normally this device used to behave, the data which we logged before is different from the data is generating now, then we could detect that. We can say that, okay, this device is not behaving properly because either there is a fault in the system itself or it has been attacked. So it's a kind of a pattern we see when a device is attacked by cybersecurity. So when I look at fingerprinting, let me give you a couple of steps how to create a fingerprint and how to use those fingerprint in authentication steps. So in the first step, we can see to create a fingerprint, we need some raw data, which is either a traffic dump from at a router level from the devices, which the traffic they are sending out, or it could be logs from the device itself. And we extract features from that raw data to create the fingerprint, because everything which a device generates is not useful for creating a fingerprint. So this is a selective mechanism, and there's a significant research has been done what features can uniquely identify a device, and these are different for different devices. So there's a vast research in this direction. Once you find out what features can uniquely identify this device using this fingerprinting mechanism, we create a fingerprint. There are different mechanisms to create that fingerprint. It could be a statistical method, or it could be a machine learning model based on the data. Once we create that fingerprint, we store that as a template in our database. So every time next time you would like to validate this IoT device against its fingerprint, you again capture the same features, you create a new feature list and create the similar way. You create a fingerprint and now you compare this live fingerprint you created with the stored fingerprint. If those two fingerprint matches, it means your device is behaving the same way as it's supposed to behave. If the fingerprints mismatch, it means the new fingerprint is not representing the same traffic or behavior it's supposed to, and something is wrong with the device. Either device has got faulty, or device has been attacked by cyber attack, or a malware is generating extra traffic, or so on, and it need it triggers a warning to administrator or device owner. So when we're selecting the features for a fingerprinting, these are the most important part when we create a fingerprint. Here I have kind of tried to separate them into two levels. One is a hardware features and software features. Some fingerprinting mechanism use hardware feature, which you derive from the hardware of IoT devices or a network interface card, whereas a software feature you extract from a MAC layer or a network or application layer. It means we are analyzing this from a standard TCP/IP stack point of view for those IoT devices. And because this figure also says that which point we are extracting those features. So sometimes we extract those features at the device itself, but sometimes we extract those features at the gateway or network layer, or sometimes at the low end at the server level. So that also makes different fingerprinting approaches different based on what features we are taking into consideration and where we are doing that fingerprinting process in the network. So there are different fingerprinting methods or terminologies when we talk about fingerprinting. Some of these I have described in one of these research paper. You can read this for more detail, but I will give a quick overview here. So for example, first is active and passive fingerprinting. Active fingerprinting means we to generate a fingerprint, we trigger the device, whether we interact with the device in some way to generate the different behavior which we would like to capture for fingerprinting. Whereas in passive fingerprinting, we are not interacting with device for the purpose of creating fingerprinting. We just observe the normal behavior of device and we just get that data to create a fingerprint. In static and dynamic fingerprinting, it's more of the features which we use for fingerprinting. So if it's a static features, or means once we define these are the feature we are going to create our fingerprints, we keep them static, whereas the dynamic features, the feature itself keep changing over time. Adaptive and fixed fingerprinting algorithm, our algorithm which we are using or our mechanism which we are using to create a fingerprint, that is a fixed or that keeps changing over time as well. Rule-based or machine learning-based fingerprinting, whether this is statistical or rule-based fingerprinting, depending on what features we have, or we use a data-based data-driven, for example, machine learning model to use or capture the irregularities or different traffic patterns from to create a fingerprint. Finally, there are two other categories. One is a white box and a black box fingerprinting. In white box fingerprinting, we have access to the software and the device itself, and we create a fingerprint at the device level, whereas in a black box, we don't have access to the device itself. It means if we go back in this network, because we don't have access to this device, we cannot do the fingerprinting at IoT or device level. We have to go and do fingerprinting at network or a cloud level. So it means that's a black box testing. Finally, based on output of the fingerprinting categorized as a unique device or a type or class, whether the fingerprinting mechanism which we design can uniquely identify device or uniquely identify the type of device or a class of device, means similar kind of devices are together. And another way of categorizing this is whether when we were doing machine learning based fingerprinting, whether the machine learning model we are using are supervised or unsupervised machine learning algorithms. Behavioral fingerprinting based on the network traffic. So now I'd like to give a little bit more idea how we use fingerprinting, which is based on the network traffic. So when we use the fingerprinting to capture the network traffic, and based on that network traffic, there are two ways we can use the features from the network traffic. First is a packet features, or second is flow-based features. So packet-based features use the content of individual packet payloads and headers, whereas flow-based features use temporal features of multiple packets coming from the same device. Is it packet flow directions or inter-arrival packets or inter-packet length? So one of the fingerprinting algorithms mechanism we recently worked on is published in one of the research paper here, used passive fingerprinting as in terms of we were just observing the traffic of the device. It uses the static features. It also uses the fixed fingerprinting algorithm. We were using machine learning models to create the fingerprint. We use the black box approach, and also we used this fingerprinting mechanism was able to identify type and class and was unsupervised machine learning model. So if when we look into the features in a little bit more detail, you can have a look. You can see that we were using a number of flow-based features here, which includes even a number of interpacket interval, or a number of packet sends or receive, variance of interpacket interval, skewness of interpacket interval, and so on. There are a number of different features rather than individually identifying the packets. This figure gives us an idea about how we created a fingerprint and what was their accuracy over time. So we used a different machine learning models. One is called naive Bayes or random forest classifier. We use conversion to 2D convolutional network. We also use decision tree classifier, and also the fully connected networks, neural networks. And this figure shows that we captured the IoT data for 27 weeks. And in this 27 weeks, we divided into three parts. So there were some 7 to 8 weeks data we used for training phases, and we picked this training data from a different weeks. And then when we validate this training data where the new biometrics for a live biometric creation, we found that when we use the training data and validation data on the same week, our accuracy of our biometric was quite high, means our classification was quite high. Whereas if we use data from a different set of timeline, and we for a training and then for a testing purpose, we use a different timeline data, our accuracy was not that great. And we found this along, no matter which algorithm we use, this was the same observation for all algorithm, all machine learning models. So that the takeaway point from here, what we learned is that if you're using a fixed features, you cannot create a biometric of IoT devices which could have a same accuracy for a longer period of time. You have to keep updating the biometric itself over the time to keep its accuracy, because the IoT device traffic varies quite different, even with the different weeks. So it's important to keep updating that. So once created biometric is not useful for that kind of approach. So here I quickly give you a recap what we have discussed in today. So we looked different views of an IoT ecosystem from a user view and from a system view. User view, we talk about how an IoT user see an IoT product, what are the values or metrics they look for, which includes usability, utility, and trust and security. From a system view, we use end-to-end ecosystem starting from different computing technologies at the sensing or actuator level, then different communication technologies, then different server and cloud computing technologies, and finally visualization technologies on mobile and cellular phones and browsers. So all those technologies come together to provide a end-to-end IoT ecosystem. And there are resilience and robustness are key factors, along with the security, in building the trust of the user to use those technologies. Then we also looked quickly on the different fingerprinting techniques for IoT devices, and there are different terminologies. And what that means is that give you a little bit idea about when someone talk about one of the IoT fingerprinting, you can easily put into framework where does it fit, like how one fingerprinting technique is different from other fingerprinting techniques, what features they are taking, what kind of algorithms or mechanism they are using to create a fingerprint. So I hope that work was a helpful work in guiding and understanding the whole IoT fingerprinting mechanism for creating the device identities, and authentication can be used in authentication process. Finally, I'll talk about creating a fingerprint using a fixed features, using the network flow, and showed how the efficiency of that fingerprint or accuracy of that fingerprint degraded over the time, and therefore we need adaptive fingerprinting mechanism for IoT devices if we would like to create fingerprinting, if we'd like to use fingerprint for cybersecurity in IoT devices. Thank you so much for listening. And if you have any questions, and if you're doing further research in IoT or any of the topics which I have discussed, feel free to email me on my email ID or follow me on my Twitter ID. Thank you so much for having me today. Bye-bye.